Welcome to this explainer. Today, we're going to decode exactly how computers think, and we're going to do it by breaking down the hidden mechanical gears of something we literally use every single day, usually without a second thought: numbers.
Before we dive in, let's ask a really fundamental question. Have you ever wondered why digital hardware relies on this seemingly alien language of ones and zeros, instead of the familiar 10 digits we grew up with? It feels like magic, but I promise you, it's just math.
Here's our roadmap. We've got 5 quick stops today. First, the familiar decimal system. Second, rules of positional numbers. Third, binary, the computer's language. Fourth, translating binary and decimal. And finally, hexadecimal, the programmer's shorthand. Let's get into it.
Section 1. The familiar decimal system.
Let's kick things off with the hyperfamiliar. When you look at the number 83, your brain naturally just reads 83. But honestly, it's a mathematical formula in disguise. It literally means 8 tens plus 3 ones. Mathematically speaking, that's 8 times 10 to the first power plus 3 times 10 to the 0 power. And the exact same logic applies to much larger numbers too, like 4,728. 4 thousands, 700s, 2 tens, and 8 ones.
Because of this structure, position is absolutely everything. In that number, 4,728, the 4 is what we call the most significant digit because it represents the thousands. It carries the highest weight. Conversely, the 8 all the way over on the right, that's the least significant digit, simply because it just represents single ones.
Section 2. Rules of positional numbers.
So, stepping back from base 10 for a second, we realize it's actually just one specific flavor of a much broader universal concept called a positional number system. To really grasp this, we've got to define the radix, or the base. The radix is the foundational number of a system. Think of it as the base multiplier for each position. It dictates the maximum value a single-digit position can hold before it, bam, flips over into the next higher position. In base 10, the max value a position can hold is 9. The second you hit 10, you flip over into the next position to the left.
The really crucial takeaway here is that there are universal rules for positional systems. Numbers are represented by a string of digits. Each position has a weight based on that radix we just talked about. The leftmost digit is always the most significant. And a radix point, what we typically call a decimal point in base 10, separates the integers from the fractions. These are the mechanical rules of counting, and they apply absolutely everywhere. Whether you're using a base 10 decimal system, a weird base 7 system, or the binary language of computers.
Section 3. Binary, the computer's language. Which brings us perfectly to base 2, the native language of computer hardware. It's actually super easy to contrast our human decimal language with the computer's machine code. On one side, base 10 uses digits 0 through 9. But on the other, in binary or base 2, the whole shebang is stripped down. Because of the physical limitations of digital computer hardware, everything is reduced to a simple on or off state, represented entirely by ones and zeros.
But here's the cool part. Those universal rules we covered, they apply flawlessly to base 2. You have the exact same positional logic at work, but instead of multiplying by powers of 10, it's powers of 2. Look at the math. A binary 1, 0 is 1 times 2 to the first power plus 0 times 2 to the 0 power. Add that up, and binary 1, 0 is actually equal to a decimal 2. A binary 1, 0, 0 is equal to a decimal 4. The math is totally identical. Literally only the base multiplier has changed.
Section 4. Translating binary and decimal.
All right, so we know the rules are the same, but how do we actually translate these numbers back and forth? To convert our base 10 integers into the computer's base 2, we use the surprisingly simple algorithm of repeated division by 2. You divide the number by 2, record the remainder, take the new quotient, and divide by 2 again. And then you just read those remainders from bottom to top.
Let's try converting the decimal number 11 into binary. 11 divided by 2 is 5, with a remainder of 1. Then we take that 5. 5 divided by 2 is 2, with a remainder of 1. 2 divided by 2 is 1, remainder 0. Finally, 1 divided by 2 is 0, with a remainder of 1. If we read those remainders from bottom to top, we get 1011. Decimal 11 is exactly 1011 in binary. It is just incredibly elegant.
Section 5. Hexadecimal, the programmer's shorthand.
Now, while binary is a perfect fit for digital hardware, it introduces a pretty major problem for the humans actually trying to program it. As the source text points out, no matter how convenient the binary system is for computers, it is exceedingly cumbersome for human beings. Just imagine trying to debug software by reading massive, bulky strings of millions of ones and zeros. It's incredibly tedious, it completely strains the eyes, and it's highly error-prone for professionals trying to work with raw data.
The clever solution to this very human problem starts with a really fun term, the nibble. Yep, a nibble. It's simply a grouping of 4 binary bits. By grouping bits into 4s, we can start to compress that endless ocean of binary data into much more readable chunks.
And that leads us straight to base 16, better known as hexadecimal. A 4-bit binary sequence gives us exactly 16 possible combinations, representing decimal values 0 through 15. Hexadecimal assigns a single symbol to each of those combinations. For 0 through 9, it just uses the familiar digits, but for 10 through 15, it cleverly swaps in the letters A through F. So, a decimal 10 is an A in hex, a decimal 15 is an F. This gives programmers a phenomenally compact shorthand.
Hexadecimal pairs sew perfectly with binary because, in most computers, binary data already occupies multiples of 4 bits. That means any long sequence of binary naturally chops up into single hexadecimal digits. It is such an efficient system that an experienced programmer can mentally convert long visual strings of ones and zeros directly into hex shorthand without even writing a single calculation down. It's basically a superpower.
Now that you've unlocked this translation across decimal, binary, and hexadecimal, I want to leave you with a really fascinating thought to ponder. Consider the actual device you are using right now. Is all the complex digital magic in your life, every single text message, every high-definition image, and every video, ultimately just an illusion built on these simple positional math rules repeating millions of times a second? Think about that the next time you look at a screen. Thanks for joining me on this explainer, and keep learning.